All right, welcome back to TalkTensors. You know the deal, right? We dig into the latest machine learning research, the stuff that's going to shape the future of AI. Break it down, make it clear, and most importantly, figure out why it matters to you.
You got it. We're your guides through the dense jungles of academic papers, helping you navigate the complex world of machine learning so you can keep your finger on the pulse.
And today, that pulse leads us straight to a paper, paper.pdf. We're going to be referencing the work of Zikon Lee here. The paper's focused on this fundamental question. How reliable are these LLM-based agents when they're out there, using tools to interact with the real world? Can we really trust them to follow the rules, to stick to those operational routines, respect constraints, and adhere to all those safety protocols? This is crucial as AI starts to take on real-world tasks, you know?
Absolutely. We're talking about things like software engineering, web browsing, even scientific discovery. Imagine an AI coding assistant that just ignores version control, or a web agent that clicks on every malicious link it sees. The potential for disaster, that's what this paper's getting at.
Yeah, no kidding. So our goal today, right, is to really unpack this research, understand how they're evaluating this critical aspect of LLM agent reliability. Okay, so let's jump right into paper.pdf. What's the core concept they're exploring?
All right, so at the heart of this research is their evaluation framework. They call it AgentOrca. And what's particularly insightful is their dual system approach. They've set up these two parallel scenarios. Think of it as a sort of control experiment. In one scenario, they've got what they call the program system.
Okay, what's that?
Basically, it's where all the operational routines, all those constraints are laid out in precise executable code. It's like the ultimate rule follower. It sets the benchmark.
Like a perfect coded rule book for the AI, huh?
Exactly. Now, on the other hand, you've got the pump system. In this one, the LLM agents get the same rules, the same constraints and routines. But instead of code, they receive it in natural language. Like, hey, make sure that the transfer amount is less than the account balance.
I see. So it's like they're trying to bridge that gap between human instructions and the precise execution that you need for AI to be reliable.
Precisely. Then they run both systems through the same environment, same tools, same data, and they compare how they perform.
So AgentOrca measures compliance by looking at the differences between these two systems.
Yeah. They examine the execution trajectories, the sequence of actions that each system takes, and the final state of the databases. Any deviation from the program system's perfect rule following, that gets flagged.
It's a clever way to automate the assessment of, how well the agent is following the rules.
Yeah.
So what makes this AgentOrca framework so significant? What's the big contribution here?
Well, the key thing is that it provides a pipeline, an automated pipeline that can be scaled up to test adherence to routines and constraints. You see, current methods often involve a lot of manual checking, which is time-consuming and not always consistent. AgentOrca brings rigor and systemization to this process.
And that scalability, that's super important as these agents become more complex and are used in more diverse situations, right?
Absolutely. Plus, the author suggests that this could even be extended to an online reinforcement learning environment. Imagine giving these agents real-time feedback, step-by-step rewards for sticking to the rules as they interact. It opens up a whole new avenue for research into training more compliant AI.
It's like moving from a post-game analysis to real-time coaching. Fascinating stuff. So to dig a little deeper here, what are the specific capabilities that AgentOrca focuses on evaluating? What are they looking for in these agents?
The paper really emphasizes two key capabilities. First, the agent has to accurately identify which constraints are relevant in a given situation. Then it has to select the appropriate verification actions to check if those constraints are being met.
Wait, verification action, what are those?
So you've got the main action, the service action, as I call it. This is the thing the user actually wants to do, like transfer funds. But before you do that, you often have to verify some stuff, like, is there enough money in the account? So verification actions are separate actions that are specifically designed to check these constraints. They're different from the service action itself.
I get it. So it's not enough for the agent to just know the rules. It has to know when and how to apply them through these verification steps.
Exactly. The second capability is strong reasoning. The agent needs to figure out the correct sequence of actions to achieve a goal, while satisfying all the constraints. And it has to correctly interpret the results of those constraint checks to decide whether to proceed with the main action.
So it's a combination of knowing the rules, knowing how to check them, and then making smart decisions based on those checks. This AgentOrca approach, it feels really novel. How does this fit in with the history of research and language agents and tool use? Like, what were the key areas of study that kind of paved the way for this work?
Okay, so to understand where AgentOrca sits, we got to look at the field of language agents and tool use. There have been a lot of benchmarks developed to see how well language agents can use tools, plan, and solve tasks. These benchmarks, they often focus on whether the agent can generate the right code to call a function or if it can successfully fulfill a user's request.
So the focus has primarily been on, like, task completion. Can it get the job done?
Right. And the authors of this paper point out that these benchmarks often miss something crucial. They often overlook whether the agent adheres to operational routines and executes actions in a compliant manner while completing the task. They're arguing that simply finishing the task isn't enough. It has to be done safely,
Correctly.
following all the procedures.
Yeah, it's like you could technically complete a task, but skip all the important safety checks along the way.
Exactly. They mentioned this benchmark called Bench, which does incorporate domain policy, but they also point out that creating those benchmarks is a ton of work. It's labor intensive, and their scope is often limited. They're not very flexible. AgentOrca, it's presented as a much more automated and scalable alternative.
So it's filling a gap in how we evaluate these agents, bringing that procedural compliance to the forefront in a more robust way. Now, moving beyond tool use, there's also a lot of research on how well LLMs can follow general instructions. How does AgentOrca connect to that area of research?
Right, so instruction following is a huge part of LLM research, and there's been a lot of work on how well models adhere to different types of instructions and prompts. For example, you've got SysBench, which looks at system messages that guide text generation. Then there's iTheval, which tests the ability to follow simple instructions like writing style or length. And then there are benchmarks like WizardLM and ComplexBench, which focus on more complex text generation tasks that have multiple constraints.
So there's been this emphasis on testing if models can follow rules when generating text.
Yeah. But AgentOrca, it shifts the focus. It looks at the dynamic aspect of following constraints during action execution in an environment. It's not just about generating text that follows a rule. It's about the sequence of actions an agent takes and whether it's adhering to the rules at each step as it interacts with tools and the environment.
That's a subtle but really important distinction, especially as these agents become more autonomous.
Yeah.
Okay, one last piece of the historical puzzle. Language agent safety. How does AgentOrca fit into that bigger picture?
As LLMs become more capable, right, they evolve into agents that can actually take actions in the world. So safety concerns, they start to extend beyond just the text they generate. It becomes about the actual impact of their actions in these dynamic environments.
Yeah, there's been a lot of talk about the potential risks of these autonomous agents.
Absolutely. And the paper references a lot of work in this area. Things like Agent Dojo and Inject Agent, which look at prompt injection attacks that can happen through tool calls on untrusted data. Then you've got ToolSword, which investigates broader safety challenges related to tool learning, things like harmful queries and risky tools. There's also Privacy Lens, which examines potential privacy leaks through agent actions, and ToolEmu, which uses LLMs to simulate tool execution and identify unsafe behaviors.
So there's this whole body of research that's trying to figure out how to prevent these agents from doing harmful things and how to secure them against malicious inputs.
Right. But the creators of AgentOrca make a really important distinction. While a lot of that previous work focuses on behavioral safety and preventing harm to the environment, their framework is specifically looking at operational compliance. It's evaluating whether agents are sticking to the defined routines and constraints during the execution of their tasks. Regardless of whether those tasks are inherently harmful or not, it's about following the procedures correctly.
So even if an agent isn't intentionally malicious, it could still cause problems if it's not following the proper procedures. And that's what AgentOrca is designed to catch. All right, now that we've got this solid understanding of the importance of this research and its historical context, let's get into the nuts and bolts of AgentOrca itself. The paper talks about these action constraint mappings. What exactly are those all about?
Okay, this is where the framework gets really interesting. So think about how we do things in the real world.
Right.
There are often prerequisites that need to be met before you can complete a main action. AgentOrca formalizes this idea with action constraint mappings. They define a service action as the main request the user wants fulfilled, like transfer funds or renew my vehicle registration.
Okay, makes sense. And these service actions, they would use specific tools within the environment, right?
Right. Exactly. Now, each service action has a set of constraints. These are the necessary requirements that have to be satisfied before the service action can be executed. For example, to transfer funds, a constraint might be that the transfer amount can't be more than the available balance. Each of these constraints is checked through what they call a verification action, which also uses a specific tool. So in our example, the verification action might be to check the user's current account balance using the banking tool.
So it's a layered system. You've got the main action, the rules governing it, and then the steps to check if those rules are being followed.
Precisely. And they formalize these relationships with two main mappings. First, you've got the service action to constraint mapping. This links the service action to the set of constraints that apply to it. Then you've got the constraint to verification action mapping. This specifies which verification action should be used to check a particular constraint.
Can you give us a more concrete example? Like, how do these mappings work in practice?
Sure. Let's say the service action is schedule a driving test in their DMV environment. Some constraints might be: the user has to be logged in, they have to be over a certain age, and they have to have passed the knowledge test. For each of these constraints, there would be a corresponding verification action. So for logged in, the verification action might be to check the user session. For over a certain age, it might be to check their birth date. And for past the knowledge test, it would be to check their test records.
Okay, so the system knows for each service action what rules apply and how to check them. What happens next?
So once a service action is requested, the agent has to call those verification actions to make sure all the constraints are met. And what's interesting is that these verification actions might have their own prerequisites. They might need to call other actions. So this creates what they call verification action routine.
So it could be a whole chain of actions,
Yeah.
a whole process before you even get to the main action.
Right. Then you've got the constraint verification outcome. Each individual constraint, it either gets verified or it doesn't. But most actions have multiple constraints. So they also define how these individual outcomes are combined to determine the overall outcome for the service action. That's what determines whether or not the agent should proceed with the main action.
And how do they handle the fact that some constraints are related in different ways? Like sometimes you need all the conditions to be true, and sometimes you just need one of them to be true.
Yeah, great question. To handle that, they have these constraint composition types. 4 basic types. First, there's single, where there's only one constraint. Then you've got and, where all the constraints have to be true, like you have to be a certain age, A and D have passed a test. Then there's or, where just one of the constraints needs to be true, like you can provide either a password or a social security number. And finally, there's chain, where the constraints have to be satisfied in a specific order, like you have to verify your registration before you can renew your insurance.
So they've got a way to represent not just individual rules, but also how those rules interact with each other. Okay, so we've covered the basic concepts of the framework. Now, how does it actually go about evaluating these agents? What are the key components of the evaluation process?
So as we discussed, AgentOrca focuses on 2 main things. First, whether the agent executes those verification actions in the right order, essentially following the routine. And second, whether it makes the right call about actually executing the main action based on the results of those verifications.
And this dual system approach, with the program system acting as the oracle, that's what makes this evaluation automated and scalable, right?
Exactly. They can automatically spot any deviations from that perfect rule-following behavior.
They also mentioned something called a directed action graph in the paper. What's that all about?
Ah, yes. That's a really cool way they visually represent the required sequence of actions and their dependencies. The nodes in the graph, they represent the different actions, both verification and service actions. And the edges, they show the prerequisites. Like if you need to be logged in to do something, there would be an edge from the login action to that other action.
So it's like a flow chart of the correct procedure.
Exactly. And the framework uses this graph to compare the agent's actual actions to what it should have done. If the agent skips a step or does things out of order, that gets flagged. They even have some really nice visualizations of these graphs in the appendix. You can really see how complex some of these routines are.
All right, so we've got the framework, the oracle, the graphs. But to actually run these evaluations, they need these simulated environments, right? How do they go about designing and setting up those environments?
So for each scenario, they created a Python-based sandbox, like banking, DMV, healthcare, library, online marketplace. Each sandbox has a set of tools that the agent can use, both for the service actions and the verification actions. And they have a simulated database that keeps track of the state of the world.
So these are like little controlled mini worlds for the agents to play in.
Exactly. They manually defined each tool. its name, arguments, description, and the code that implements it. They also define the constraints for each domain, how to check them, and how they map to the service actions. And they even created a template to help with generating different test cases.
It sounds like a ton of work to set up these realistic environments.
It is, but allows for this really detailed automated evaluation. They also built a special constraint checking module for the program system. This ensures that the Oracle always behaves perfectly.
Okay, so the environments are set up, the rules are defined, and we've got the Oracle.
Yeah.
But how do they create the actual test cases to evaluate the agents?
This is another clever part. They call it LM-assisted test case generation. They leverage LLMs to do this. Manually creating test cases for all the different combinations of constraints would take forever, so they automate it. The key idea is constraint permutation. For each service action, they go through every possible state of the constraints, like, is this constraint met? Yes or no? This creates a wide variety of scenarios.
So they can create cases where all the rules are followed, none of the rules are followed, and everything in between.
Exactly. Then they use LLMs to generate the user instructions and the initial state of the database that would lead to those scenarios. This is what makes AgentOrca so scalable.
It's really efficient.
Yeah.
Okay, so we've got the framework, the environments, the test cases. What did they actually find when they ran these evaluations? How well did the different LLMs do?
The results, they're really insightful. They tested several models, GPT-4o, GPT-4 Mini, Claude 3.5 Sonnet, Gemini, Qwen, and Llama, across all 5 domains. And they looked at the overall pass rate, basically how often the model followed all the rules.
And what was the overall verdict? Did these LLMs generally pass the test?
Well, the pass rates varied. One interesting finding was that most models, except for GPT-4o, did much worse when they were given all the tools for the domain. Compared to when they were given just the relevant tools, it seems like they struggled to filter out the irrelevant information. GPT-4o seemed to handle this much better.
So being able to process long context, that's really important for reliability. What about adversarial users? Did they test how the models would hold up against someone trying to trick them?
They did, and the results there were pretty concerning. They simulated these adversarial users who tried to persuade the models to do unauthorized things in the healthcare domain. And all the models, even GPT-4o, performed poorly. It shows that even the most advanced models can be manipulated.
That's a big red flag for safety, for sure. If they can be tricked so easily in a simulation, what happens in the real world?
Right. They also looked at how performance changed as the tasks got more complex, like when there were more constraints. And as you might expect, most models did worse as the number of constraints increased. But again, GPT-4o was more consistent.
So it seems like GPT-4 was more robust in those tests. What about the types of errors? Was there a pattern to how the models failed?
Yeah, they categorized the errors. And the most common one was routine violations, meaning the model didn't execute the actions in the right order, even if it got the right outcome in the end. The second most common error was incorrect judgment, where the agent made the wrong call about whether to proceed with the action. Interestingly, they found that actually using the tools, calling the functions, that part was generally accurate. So the problem isn't with the individual actions, it's with orchestrating them correctly.
The big picture thinking, huh?
Right. And they have these representative cases in the appendix. Specific examples that show you exactly how the model's messed up. Like one where GPT-4o does everything right, one where Claude misses a constraint, one where Gemini doesn't even call the final action. These examples are really helpful.
Yeah, they give you a much better sense of what's actually going on. Okay, so last but not least, the novel notions section. What are some of the potential extensions of this work? What are the next steps?
So they talk about integrating online reinforcement, learning more deeply, giving agents real-time rewards for following the rules. This could be a really powerful way to train more compliant agents from the start.
That makes sense. Instead of just evaluating them, you're actually guiding their behavior.
Another area they suggest is automating more of the process, like designing the environments and validating the data. They think autonomous coding agents could help with that.
That would make the whole framework much easier to use.
They also acknowledge that right now, they're mainly focusing on simple constraints, things that can be easily checked by a program. They want to expand it to handle more complex types of constraints.
Yeah, real-world rules can be a lot more nuanced than that.
Absolutely. And given their findings on adversarial users, they also propose using this framework to develop better defenses against manipulation. By understanding how the models fail, we can learn how to protect them.
That's a really important application of this research.
And finally, they talk about using those directed action graphs for real-time monitoring. Imagine tracking an agent's actions in real time and being able to intervene if it starts to go off the rails.
Like a safety net for autonomous agents.
Exactly. So AgentOrca is more than just an evaluation framework. It's a foundation for future research into building more reliable, safer AI.
So for our listeners out there, what's the key takeaway from all of this?
I think the big takeaway is that AgentOrca gives us this really valuable tool, a way to rigorously evaluate how reliable these language agents are. And that's crucial as we start to deploy them in the real world. The research shows that while these models are really impressive, they still have a long way to go in terms of consistently following the rules, especially in complex situations.
And understanding these limitations, that's essential for building the next generation of AI. AI that's not just capable, but also trustworthy and safe.
It all comes back to trust, doesn't it? As AI agents become more autonomous, as we give them more responsibility, how do we ensure that we can trust them to operate safely and reliably? Frameworks like AgentOrca, they're a big step in that direction. It's not just about what AI can do, it's about how it does it.
And that's something for all of us to think about. As AI becomes more integrated into our lives, that question of trust, it's only going to become more important. So keep that in mind as you follow the latest developments in the field. And stay tuned for more deep dives into the research that's shaping the future of AI.